Okay, so before I start, I want to quickly just note two things. The first one is I want to remind you guys that this series is closely following Stephen Abbott's Understanding Analysis, second edition. Hopefully that will be linked, or the name will be put in the comments, because I noticed a few of you were asking about a textbook. It has some great questions in it. It's a really helpful book. It goes in more detail than we're going, but we're following a similar structure, and of course I'm drawing from other resources as well, but that's the primary one. And then I'm thinking about, and there should be one at the bottom of this video, and hopefully in future too, of making just little handouts that really quickly just dot point what we've talked about, and maybe have some practice questions pulled out of them for those of you that don't have access to the book or anything like that. But yeah, so to get started on the initial construction of the real numbers. So this is the first construction we'll do, and as I said before, we'll come back much later on and do another one which is a little more in-depth, and that's because hopefully by then you'll have a stronger appreciation for why we would want to construct the real numbers in a more rigorous way. So last time we talked about the inf, which is like the greatest lower bound. So it's the biggest number that's smaller than all of the numbers in a subset. We talked about the sup, or the least upper bound, which is similar but sort of reflects it. So it's the smallest number that's larger than all of the other numbers in a subset. We talked about a field, which has an addition and a multiplication operator. And we talked about order, so to do with inequalities and stuff like that. And I mentioned then this little theorem here. I mentioned that if m is a maximum of s, then m is also the sup, or the sup of x. And that is actually only supposed to be one direction. My bad. Because that doesn't infer itself the other way. And we're going to go about trying to prove this today. It's not a particularly hard thing to prove, and it's fairly intuitive, but I wanted to go through it and sort of discuss proof strategies and what you'd be looking for. So the first thing I would do when looking at a question like this is there's two very, very core things. There's nothing really else to it: the max and the least upper bound. So I'd write out definitions for those. So definition of a max. So m is a max requires two things. The first one is that for all x being an element of the subset, we'll call it S, m has to be greater than x or equal to x. So it has to be larger than everything in the subset or equal to it. And the second criteria is that x itself has to be an element of the subset. Otherwise it wouldn't really be the maximum element of the subset. Definition of the sup. Again, the sup has two properties. The first one is that is actually the exact same property. So for all x being an element of S, what should we call the sup? We will call the sup A. A has to be greater than or equal to x. My pen's been sort of playing up a bit recently, so I'm getting a bit of broken text. And then the second criteria is that, this is a little bit longer, but it's just the criteria that says that it's the least upper bound. So that is for all elements less than our sup A, there exists some element in the set such that P is less than that element. So that's just saying anything smaller than that can't be an upper bound because there exists something bigger than it within the subset. Okay, so what we want to do is, using these criteria here, we want to prove that these criteria are implied. Now the first one, straight off the bat, super easy to do, so we'll just write 1 is true by definition of the max. By definition. Okay, the second one is, again, really intuitive, and this is actually one of the things that makes this difficult to get your head around, because the second one feels right, but it's harder to say that it's right. And the argument I made for this, and you could potentially make a different one, is that that second criteria here, this one here, of the sup, is satisfied because we can choose, there does exist an element of S that is larger than anything smaller than it, and that is the max itself. So I'll try writing that out, and then hopefully I'll explain it. So this is true because for all P being less than M is greater than P. That's an identity. It's just sort of a reflexive statement, quite easy, quite true. So statement 2, which state, I don't know if that's got a mint, my spelling's terrible. Statement 2 can be satisfied by x equals m. Right, so statement 2, if we choose this x to be equal to m, then we have p is less than m, and for all p being less than m, because remember, we're trying to prove that this is true for m, so all our a's turn into m. So for all p being less than m, there exists some x in the set, yes there does, m, such that p is less than m, because that's this reflexive statement here. So we've essentially cut out this guy and we've replaced this for an m, and we've ended up with this very simple statement. Why can we choose m? We can choose m because m is an element of the S, of the subset. We can do this because x is an element of the subset. Again, that's by definition. So really we've just sort of re-demonstrated the definition and ended up proving what we wanted to prove. So yeah, but the real thing I wanted to home in on was when you're trying to prove things, real analysis is really fortunate in the sense that it has these really clear, rigorous definitions. So if you want to prove something, it's quite beneficial to just write out those definitions, and hopefully things will start to fall into place and you'll see something, but that's really the starting point. So I've proved statement 1 and statement 2, so therefore the theorem must be correct. Alright, cool. So now we can actually move on to the real numbers now that that's cleared up. So the real numbers, we want a couple of things in the real numbers. I'll just add a little bit of space in. So, in the real numbers, the first property we want of the real numbers is the one that we heavily discussed last time, and that is that, it's got kind of a fancy name, but R is an ordered field So that's one of the important ones. R is an ordered field. We discussed what it meant to be an ordered field. And the next thing, which we haven't really discussed, but hopefully it kind of makes sense, is that it contains the rational numbers. And that just means that the rational numbers are a subfield. So it contains the rational numbers as a subfield. And all a subfield essentially is a subset where the algebraic structure of a field still holds true. So the addition and multiplication that we've defined for the real numbers should also work on the rational numbers, with the rational numbers being a subset. So that's kind of what's meant by an ordered field. The next thing, and really the important thing that will be quite useful for us, I'll bring it up here, is the axiom of completeness, or the AOC. The second thing the real numbers have to have is for R, in R, the axiom of completedness is true. And that's fair enough, given that the axiom of completeness says R. So the axiom of completeness says that all subsets of R that are bounded above have a least upper bound. So by bounded above, what we mean is that it's not a subset that just continues on to infinity. It makes kind of sense. And any subset that is, finite in its maximum elements has a least upper bound. Okay, so that kind of makes sense, what that means, hopefully. And we'll look at why that implies a field that is what we kind of came to think of as the real numbers back in year 8 when we first sort of discovered Pythagoras' theorem or whatever. So to do that, I'm going to go with the sort of pinnacle example of real numbers, and that is the right triangle with sides 1, 1, square root of 2. So we learn that the square root of 2 is irrational from the minute we hear of square roots. We may see the proof might be held off for later, but we've known that it is something with infinitely many decimal places. And most people know of irrational numbers today for ages with things like pi and stuff like that. You hear people who aren't even interested in maths say, oh yeah, pi goes on forever. So the square root of 2. In the rational numbers, how do we talk about a set which could somehow imply the square root of 2? And the way we do this traditionally is we say that the set S containing all elements, R being an element of, because we're talking about the rationals, such that R squared is less than 2. Okay, that's fine. That's a subset. There's a lot of R that I can think of that are less than 2. 1 would be in that subset. 1.2 would be in that subset. 1.5 wouldn't be in that subset, but 1.4 would. And you can see that sort of as the decimal expansion gets closer and closer, but still less than, our decimal approximation of the square root of 2, all of those things are going to be an element of our subset. Problem is this subset doesn't have a least upper bound in the rational numbers, because the minute I pick an element to be the least upper bound, well, I can just add a couple more decimal places, because we know the square root of 2 has, an infinite amount of decimal places. That's what makes it irrational. If it was rational and it had if it was irrational but had a finite number of decimal places, then it couldn't possibly be irrational. We could write it as a fraction over, 10 to the power of something. So I'm not going to prove that this doesn't have a least upper bound. That would potentially be a good exercise. It is kind of finicky to do. But I hope we can see that there couldn't be a least upper bound. We know that the least upper bound is the square root of 2, but the square root of 2 is not rational, so it doesn't exist within this subset. However, if we transition over to the real numbers and we define our new, basically the exact same thing, but now it's the real numbers with R squared. Well, now it needs to have a least upper bound. So now the square root of 2 needs to exist by the axiom of completeness, because if it didn't have a least upper bound, we couldn't possibly satisfy the axiom of completeness, and that is an axiom. It is the definition of the real numbers, is that it satisfies the ordered field and it satisfies the axiom of completeness. So it has to have a least upper bound, and what we're going to show, or we're going to begin to show, is that that least upper bound is exactly what the square root of 2 is. And that is just here. We are going to show that in the real numbers, the square root of 2 exists. Kind of a fun little proof to do, and I am going to leave a bit of it to you. Exercise for the reader. But, we are going to prove that if A is equal to the sup of t, where t was this thing defined just up here, if A was equal to the sup of t, A squared is equal to 2. which is essentially the same thing as saying that a is equal to the square root of 2. And because we know that a exists in the real numbers by the axiom of completeness, then the square root of 2 has to exist within the real numbers by this statement here, by proving that it's equal to 2. So how are we going to go about proving it's equal to, that a squared is equal to 2? Well, we're going to do that pretty easily. Well, it's a bit weird, but we're going to show that a squared is not less than 2 and that a squared is not greater than 2. Okay. Easy enough to see why if it's not less than something and it's not greater than something, then it must be equal to that something. But how are we actually going to go about proving that? And we're going to do this proof by contradiction. Pretty typical proof style, comes up a lot when dealing with irrational numbers. And step one, if you haven't seen a proof by contradiction, you start off by assuming that the statement is wrong. So what we're going to do is we're just going to prove this one, and I'm going to leave this one for you. I will give you a little bit of guidance. The book, Abbott's, does fill it out, I think, if I remember properly. It might leave it as an exercise as well, because it's essentially the same thing again, just with a slightly different expression. Okay, so what we're going to do is we're going to start off by doing a plus something else, 1 over n, where n is an element of the natural numbers. So it's a integer and it's greater than 0. So this expression, a plus 1 over n all squared, is going to be greater than a squared. Okay, so what we're going to do is we're going to show that this a plus 1 over n squared thing is less than 2, and that therefore if a squared is less than 2, that it's not the least upper bound, which is where our contradiction is going to come from. So a plus 1 over n all squared, I know that was a bit of babble, but hopefully it'll make sense as we go, is a squared plus 2a over n plus 1 over n squared. Fun little thing, that is 1 over n squared is going to be less than 1 over n. Well, it's technically going to be less than or equal to, but we can assume, we'll assume n is not equal to 1, so that this holds. So that means that this thing is going to be less than a squared plus 2a over n plus 1 over n, which is equal to a squared plus 2a plus 1 over n. Okay, so now we have to find a value of n, because n can be as large as we want, but we want to find a value of n that successfully, goes ahead with our contradiction. And it's a pretty specific value of n that we end up having to choose, but we want to pick a value of n, we'll call it n naught, such that 1 over n naught is less than 2 minus a squared over 2a plus 1. Okay, so now we have, give myself some more space, we have a plus 1 over n naught squared is less than a squared. Well, 1 over n naught, this n here becomes an n naught, so we can substitute that in. So 2 minus a squared, 2a plus 1 times, 2 minus a squared over 2a plus 1. So these two guys cancel, and we end up with a plus 1 over n naught squared, did I forget? No, is less than a squared plus 2 minus a squared, so it's less than 2. Okay, so a quick couple things to note. This is known as, well, it's an example of the Archimedean property, and I haven't proved that. That is, it'll be in the handout at the bottom, the proof of it. It's just that in the natural numbers, or in the rational numbers or anything like that, if you pick a number, there's a number bigger than it. So, I didn't prove it because I thought it was fairly intuitive, and hopefully you can see that you can pick an n naught large enough that it's smaller than really any arbitrary quantity, as long as that quantity is not 0. But what we've done here, in picking this value of 1 over n naught and through our algebra over here, is we've shown that if a is less than 2, if a squared is less than 2, then there exists some other number, say b, equal to a plus 1 over n naught, such that b squared is less than 2 and a is less than b, right? Hopefully you can see that b is b is bigger than a, because 1 over n naught is going to be positive. And that's a problem. That's a contradiction, because we have said that a is the least upper bound. And we've just demonstrated that if a is the least upper bound and that it's less than 2, we can find some other number bigger than it, which is also less than 2, which would then be the least upper bound. Because this larger number, this b is also going to be an element of the set. I'm running a whole bunch of random stuff. B is also going to be an element of t, and because a is less than b, a can no longer be the least upper bound. So we've shown that if a squared is less than 2, a isn't the least upper bound. And because we've said a is the least upper bound by definition, up here, a is the least upper bound, and we've just shown that it's not the least upper bound, then our assumption here must be wrong. Okay, so there we go. We've proven the first part. We've proven that a squared is not less than 2. The next part that we would want to prove, and this is the bit I'm leaving to you guys, is we want to prove that a squared is not greater than 2. And it's going to be the same deal. We are going to assume it is greater than 2, and then we're going to pick our b squared to be equal to a minus 1 over n squared. We're going to expand it out, and we're going to show that that number is smaller and it is bigger than all of the other ones. We're just going to show that b is a upper bound and that b is less than a, so therefore again we have a contradiction because a is no longer the least upper bound. And because, taking these two guys together, we have that a squared is equal to 2, which is what we wanted to prove. We've proven that in this set, T, here, if we define a to be equal to the sup of T, then a must be equal to the square root of 2. Hopefully that comes through. And by the axiom of completeness, R must contain, must contain that square root of 2. Okay, I'll run through that one time very briefly of what R is. R is an ordered field that contains Q as a subfield, and in R the axiom of completeness is true. What we've done is we've shown that if we define some subset of the real numbers as such, that the sup of that subset is equal to the square root of 2. And we went about by showing that if that sup was less than 2, we had a contradiction, and if it was greater than 2, we had a contradiction. So we had that the sup had to be equal to the square root of 2, and by the axiom of completeness, the square root of 2 has to be an element of the real numbers. I really hope that made sense. It was a bit all over the place. As I said, the handout and the description will clear things up a bit. I'll write this out a bit neater in our dot point thing so you guys can have a read through it. But yeah, that should do it. That covers everything I wanted to cover today. Next time I'm going to look very briefly at the beginning at what's known as the density of Q in R, which is to do with how often rational numbers occur within the real numbers. And then we're going to jump straight into sequence and series, because we've spent 2 videos now on setting up the real numbers. We may as well actually do something with the real numbers. But yeah, anyway, thank you, Bye.